So the inner product between two wave functions have an important physical interpretation. So we want to understand the inner product between two wave functions. So to see this, let's take an operator. For example, let's take the energy operator, the Hamiltonian. So the Hamiltonian is the energy operator. And let's look at the eigenvalue equation of the Hamiltonian. So the eigenvalue equation of the Hamiltonian is nothing but the time-independent Schrödinger equation. So let's denote the eigenvalues by En, where n is, say, some integer. It doesn't have to be an integer, but let's, for convenience, choose our label to be an integer. Then the eigenvalue equation is given by h hat acting on psi n is equal to En of psi n. Now, because Schrödinger equation is a linear equation, we know that if we have two solutions of the equation, their linear combination is also a solution. So what we can do is that we can say that, okay, all these psi n's, these are solutions to the Schrödinger equation, so we can create a linear combination of all these psi's, say C1, psi 1, C2, psi 2, plus C3, psi 3, dot dot onto infinity, where Ci's are complex numbers, they are complex constants. So this linear combination, phi, is also a solution to Schrödinger's equation. Furthermore, let's assume that we have normalized psi n's. In other words, psi n, psi m gives me delta nm. So we can always do that, of course. So then, what I want to show is that the inner product between one of the eigenfunctions and the states phi is the coefficient Cm. How do we show this? We write phi as a linear combination from 1 to infinity of Ci psi I. So this is this thing, the left-hand side of this equation. And then what we can do is that we can then take the summation out of the inner product. And you should verify that you can do that because Ci's are just constants. And inside the inner product, I have psi m and psi I. But these have been normalized and they're orthonormal, so they satisfy this equation. So I use that equation now. I is 1 to infinity Ci delta mn. So I can now do this sum easily because I've got a Kronecker delta, and that sum just gives me this should be an I. The sums gives me, wherever there was I put m. So there's an I here, there's an I here, so I put in its place m. And therefore we have proved this equation. So what is the interpretation of these numbers Cn or this inner product? To see this, let us look at the expectation value of the Hamiltonian operator H. So given in the state phi. So this is defined by integral of phi star H times phi integrated over all x. And we are assuming that phi is normalized, so we don't have to divide it by the norm of phi. So if I do this now, then what do I get? I can now expand one of the phi's as a linear combination of the eigenfunctions of the Hamiltonian operator, and then what we can do is that we can bring the Hamiltonian operator inside this sum, but h hat acting on psi I, what does it give me? It gives me EI. So here I have and then what I can do is that, assuming that both the sum and the integral converge, we can change the ordering of the sum and the integral. And if I do that, I can bring out the sum outside the integral, and I can do Ci, Ei. These are all constants. They don't depend on x, so I can bring them outside the integral. And inside the integral, I have but we know what this thing is. We derived it previously. We derived it over here. This thing is Ci, Ei, the inner product between phi and psi I. So remember that psi I, phi is psi Ci. So here the ordering has been reversed. Therefore, over here it should be 1 to infinity Ci, Ei, Ci star. So we can write this as sum over I to infinity Ei mod of Ci squared. So this is what the expectation value of my Hamiltonian operator is in the state phi. So let me compare this to what the definition of the expectation value is. So the definition of an expectation value of some random variable, is given by the sum over all its possible values, which in this case are the eigenvalues, times the probability that that value would be obtained in an experiment. So comparing these two equations, we see that P, the probability that in an experiment we will get the value EI, is given by the modulus squared of Ci, which is equal to the modulus of psi I phi squared. So this is the interpretation of the inner product between two different states.